Okay, we'll get started. So far, we have studied a lot of background material about ICs, the components that are available, what kind of errors we can have, and how to calculate those errors and so on. Okay, everything from mismatch to random noise to distortion. So now it is time to go and design some circuits. Again, you're not new to circuits. You've already seen many of these circuits in analog circuits, but we will do it in a way that is done on ICs. So now we can start with any circuit, but I would say sort of the most important analog circuit, the workhorse of analog ICs, is the negative feedback circuit, right? Lots of things are done using negative feedback, like amplifiers and so on. And you also use negative feedback just for biasing transistors and things like that. So if you take any analog IC, there will be a system with negative feedback in it, and that may be using op amps with negative feedback around each op amp. And inside each op amp, there are bias circuits with negative feedback around them and so on. So it's very important to understand negative feedback systems if you are able to, if you want to be able to design analog ICs and analog systems. Okay. And I'll say negative feedback amplifier to start with. Okay. And we can take anything that we want, but let me say I'll take a case where the input is a voltage Vi and the output is a voltage V0, and you want the output to be K times the input. Okay. So this is an amplifier. The output is some number times the input. Okay. So now what is this negative feedback all about? Of course, you know how to make amplifiers, a common source amplifier. This is the very first amplifier that you learn, and this has V0 to be minus GM RL times Vi. Okay, the number happens to be negative, but this also has output as something times the input. So what is with this negative feedback amplifier? Is it just another name for any other amplifier, or what's special about negative feedback? Okay, so K is much better controlled. Is that it? What distinguishes? Is this common source amplifier a negative feedback amplifier? Why not? There is no? Okay, what is feedback? So the key element of negative feedback, you can make amplifiers in many ways. Okay, so one is this common source amplifier. It has some property, you apply some input, it gives you an output. Okay, now the thing with negative feedback is you have a loop to control the output. What does the loop do? So basically you compare the actual output with the desired output, and depending on the difference, you drive the output in the correct direction. That is, if the desired output, if the actual output is less than the desired output, you go on increasing the output. The actual output is more than the desired output, you go on decreasing the output. Okay, so that's what negative feedback is. So it has that this business of comparison, that is some sort of comparison, right, of the actual output to the desired output, and continuously driving the output in the right direction. Okay, so the fact that you are doing comparison and driving it, that means there is feedback. Negative feedback means you drive it in a direction that reduces the error. Okay, so negative feedback means that there is some error between the desired and actual outputs, and if you drive it in a direction that reduces the error, that means you have negative feedback. Okay, is this fine? So now let's try to implement this. Many of these things you already know, but it's good to have a review and perhaps an alternative viewpoint to what you already know. Okay, so this involves compare the actual output desired output in some form, and then try the output in a direction that reduces the error. Okay. Again, this is something that you would have used in basic biasing circuits as well. Okay. Now let's say this is the relationship I want to have. This basically means that when I say I have VI, that you can imagine that there is some voltage VI that's available to us, and I want to produce voltage V naught somewhere. Okay. So now how do I go about doing these things? What is it that I need? If I want to implement this relationship using negative feedback, what should I do? So obviously you have to compare the actual output to the desired output, but clearly we can't compare V naught to K times Vi, because if you already had K times Vi, you won't be making the circuit in the first place, right? But this means that really you should have some measure of this, which is desired output minus the actual output. Okay, it doesn't have to be this. If you divide this by K, you will get Vi minus V naught by K. Okay, so it will have the same polarity as KVI times V naught, right? So you can implement either one. You have to see which one you can implement in a given situation. So in this case, we will compare you compare Vi and V naught by K. Now, of course, V naught by K is easy to generate. You use a resistive divider and you get V naught by K, right? Huh? Right. We are making an amplifier, so we assume that K is greater than. Well, correct, but then do you need to make a circuit? That's the question. K is less than 1, right? So it's an attenuator. You may not need to have amplifiers and so on to make that. You may be able to do it in a purely passive way. Okay. But yeah, if you do have gain in the feedback network, you will have attenuation in the closed loop system. So now we compare, that means we take the difference between these two and we get some error voltage, which is Vi minus V naught by K. Now what should happen to V naught? How should V naught change with VE? What should happen to the output if VE is positive? Output should, if Vi is positive, what should happen? If Vi is positive, what does it mean? The output is too small or too large? It's small, it's smaller than required, right? So the output must go on increasing. Similarly, if V is negative, the output should go on decreasing. This continuous adjustment is key to negative feedback, right? The thing is, you don't know exactly how to sort of control the output. Okay, the analogy I often give is that of driving. So if you want to drive at 40 kilometers an hour or some speed and you're driving a car, it's not as though you know exactly how much to press the accelerator so that it goes there. What is it that you do? You will constantly look at the speedometer, and if the speedometer reads less than 40, you go on accelerating. If the speedometer reads more than 40, you go on braking. Okay, so the continuous adjustment is what you do, right? It's not as though if you press your foot down by like 15 millimeters, it will go at this speed, and I mean, it doesn't work like that. Okay, so the same goes for many other processes in our life. We constantly use this negative feedback. That is, we make continuous adjustment based on some comparison, right? You want to adjust the volume of your sound system so that the volume is comfortable to you. Again, you go on adjusting it. You don't set it to, let's say, number 5 and then assume that it's always right. Okay. So this continuous adjustment based on the comparison is key to negative feedback. Okay. So now the question is, what should that block be so that you get this continuous adjustment? What should it be? Why? What should that be? Why? So again, the easiest thing to imagine is that the feedback is not there. Okay. Again, in the driving analogy, what happens if the feedback is not there? First of all, right? So let's say this is 0. So you're getting a constant input. Okay. So similarly, you can imagine driving with a stuck speedometer. The speedometer is stuck to some value, and you have, let's say, no other perception of speed. Okay. Not a good way to drive, but anyway, let's for the sake of this analogy, it's fine. So then what will you do if the speedometer is stuck at 20 and you want to go at 40? Huh? So let me call this VFB, okay, for the feedback voltage. So let's say this is now so this is analogous to the input and this is analogous to the feedback quantities, right? So the error is constant. Okay. So now if you drive the way that we just described, what happens to the actual speed? Because you think the speed is not increasing, you will keep the accelerator jammed to some level and then the output or the speed goes on increasing. Okay. Now, of course, it can do it in any way. We'll assume a linear dependence. So basically, what we are saying is that if the error is constant, the output is constantly increasing. Okay. It doesn't have to be a linear relationship, but here we'll assume that it is linear. So now what is it? What is a block that gives you this relationship? It's an integrator. Okay. So this must be an integrator. Have you already seen this treatment of the negative feedback as an integrator in the earlier class? I mean, look, thinking of negative feedback as an integrator in the earlier class, was it done like this or you're already familiar with this? Huh? Analog systems. Okay, fine. So basically, what this integrator does is, as long as the input is positive, the output will go on increasing. When the input is negative, it will go on decreasing. Okay. It will stop when the input is 0. Okay. So what makes it stop is this comparison, right? When this comparator, when the result of this comparison goes to 0, that's when it stops. Okay. So that is what negative feedback is, right? Is this okay? So now this is basically what we want to implement. So let's say we have Vi. Since you already know this, I will. So this has to, there has to be some constant here that appropriately relates the input and the output. In this case, the input is a voltage, the output is a voltage. So this whole thing has to be dimensionless, and I have that number has dimensions of omega u. Okay. Of course, if you represent this in the Laplace domain, it will be omega u by s. Okay. So this is the integrator. What will be this omega u integral dt or omega u by s? What will be the Bode magnitude plot of this transfer function? What is it? Straight line with minus 20 dB per decade. And at what frequency does it cross unity? 0 dB. I mean, what frequency does it cross 0 dB? Omega u. Okay. So this omega u, if you look at this frequency domain interpretation, it is the unity gain frequency of the integrator. It's the frequency at which the gain magnitude of the integrator becomes unity, right? Just for completeness, what is the angle of this transfer function? It is minus 90 degrees throughout. Okay. Is this fine? So the time domain interpretation is also important. So let's say if the input is a step, what will be the output? If the input to the integrator is a step, what will be the output? It will be a ramp. What will be the slope of the ramp? What is it? Omega u times V, right? Now, if you increase omega u, what happens? It will ramp up faster, where omega u prime is greater than omega u. Okay. And similarly, if you had a larger omega u, it would just like get shifted up like that, right? So that is omega u prime. Okay. So in the frequency domain, the unity gain frequency increases, or in the time domain, the ramp gets more rapid. Okay. So this again, you can see like how to, I mean, from the analogy we're driving, I mean, you can try to change the speed rapidly or slowly. Okay. So that is characterized by this omega u. So if your omega u is large, then you will reach your goal more rapidly, and if your omega u is low, you will reach it more gradually. Okay. So it's a measure of how rapidly the integrator tries to reach the output. Okay, tries to drive the output towards the desired value. Okay. Now, what is the closed loop transfer function of this V naught by Vi? Please calculate. What is the closed loop transfer function of that negative feedback system? 1 by? Yeah. So what is it? Please calculate. Probably remember the result. If not, just calculate and see. Yeah, many ways to do it. Again, you have done control systems, right? Or you're doing it now? You've done it. Okay. So in the standard control systems terminology is to, what is this block and what is this block? What do you put inside here? In control engineering. What is in the upper block? What is in the lower block? Huh? G and H. Okay. And what is Y by U? G by 1 plus GH. Okay. So these things are worthwhile remembering. It's a shortcut. In our case, G is omega u by S and H is 1 by K. So basically you can write it as omega u by S by omega u by S plus 1 by K times omega u by S plus 1. This is not a very nice form. So a couple of different ways to write it. This can be written as K 1 by 1 plus S times G by omega u. Okay. So this is a useful form in that this gives you what we were trying to achieve, right? Ideal gain. And this is something extra, we'll see. Okay. Now earlier I said that if the input is constant, if the input Vi is constant, what will be the steady state output? If the input is constant, what will be the steady state output? K times the input. It has to be, right? Otherwise, what happens is this error is non-zero and the output will go on changing. Okay. So now in this expression, what is the meaning of saying that if the input is constant, how do I look at the output? What should I do? S equals 0. So that corresponds to DC, right? So that means for DC, this is ideal. You get a gain of K, right? That's what we get from the time domain reasoning also. So now we'll see, we'll sort of turn this over in many ways and then see again something you're familiar with. So now, first of all, what will the Bode plot of this look like? This is V naught by Vi, and if I plot the magnitude of V naught by Vi, what will that look like? What is it? What is it at low frequencies? Yeah, K. I'll just write it as K. And then what happens at omega u by K? It starts falling. Okay. And of course, if you plot the phase, I won't always do that. For this case, I'll show. So the phase will reach minus 45 degrees at omega u by K and eventually reach minus 90 degrees. This is the angle. Okay. So now what is with this omega u by K? Is it, I mean, of course we got it out of the calculation, but is there some significance to that? What is that? Huh? It's the 3 dB bandwidth. I mean, that's the result we have got, but is there any significance to that result? No, I know, but that we are essentially describing this curve, right? I'm saying in the negative feedback loop, is there some significance to this number? What is this number? Huh? Pardon? That's correct. So, of course, if you apply a step to this, if Vi equals Vp u of t, what will be the output? I mean, let's say from 0 initial condition, what will it be? Huh? It will be kvp 1 minus exponential. Of course, this is again, we are still describing the system. If you have 3 dB bandwidth of omega u by k, you will have that also in the exponential of the step response. Okay. So now let's look at this negative feedback system in some if I use the standard control system terminology, y by u is g by 1 plus gh, which can be written as 1 by h, gh by 1 plus gh. And typically I use, what is this gh actually? What is it? Loop gain. I use L as a shorthand for gh. Okay. What is this loop gain? Yeah, what loop gain is basically you break the loop somewhere, you apply some signal and see what comes back. It is basically something that quantifies the amount of feedback. Okay. So if you look at this, you have 1 by h, L by 1 plus L. I mean, I could keep gh also, but typically we don't use this gh, so I won't do that. So now, when the magnitude of L is much more than 1, how do you approximate this? What will this be? 1 by h. Okay. And when the magnitude of L is much less than 1, what will it be? Or actually, here, maybe it is more enlightening if you do this. In this case, if the magnitude of GH is much less than 1, what will be the output? Huh? G. Okay. So that is so fine. We've got some approximation here. What's the significance of this? What does it really mean? Okay. So what is really happening? So let me maybe just rewrite this. Okay. So first, maybe this is easier. What is the interpretation of that? Yeah, basically what it says is, it's not enough to have some wire coming back from that side to this side, right? There has to be a significant signal coming back. If GH is much smaller than 1, it's as though the feedback is not there. Simply you get U times G equals Y, that's all. Okay, you have only the forward path. So this is what happens when the loop gain is much smaller than 1. Anyway, that is not the area of interest for us. That is, when you make negative feedback systems, all the good stuff about negative feedback systems comes because of loop gain. Okay. So here you see, interestingly, that if GH is much more than 1, when the loop gain is much more than 1, the gain does not depend on the forward path. Okay. So that is what is good about this negative feedback system. So this is why, to make robust feedback systems, what you do is you have H set precisely. Okay. So that may be in our amplifier's case, H is through the resistive divider. Okay. So 1 by K, that is set precisely. G should be such that you get a very large GH. G doesn't have to be precise. Okay. That's the idea. So for instance, this, if you look at this expression, regardless of what omega u is, the DC gain is going to be K, right? So you don't have to worry about how much the loop gain is, as long as it is large. Okay. So now, what is the loop gain for this particular system? What is the expression? What is G? What is H? So what is GH? Omega u by Ks. Again, I'll represent it this as L of S. Okay. So now, if I plot, so I know that L of S is omega u by K times S. So if I plot the magnitude of L, what will I get? Huh? Straight line. Then what is the significant part of the straight line? So it It is a straight line with a minus 20 dB slope, and it crosses unity at omega u by k. Okay. So earlier we had got omega u by k there. Now we have got it there. Now is there any relationship, or is there one more coincidence? What did we want the amplifier to do? I mean, we wanted the amplifier, I mean, we designed the amplifier, we made the negative feedback system to do something. What was it? We wanted an amplification, we wanted a gain factor of k, right? So now you can see where the loop gain is significant, that is to the left side of this omega u by k, you have a closed loop gain of k. Where the loop gain is insignificant, it goes haywire. Okay. Now, of course, the loop gain is falling gradually from very large values to 1 and then smaller than 1. Okay. But if you had to sort of put a dividing line between loop gain is significant here and not significant there, that's the unity loop gain frequency. Okay. So the unity loop gain frequency will be roughly the closed loop bandwidth of the system. That is, below the unity loop gain frequency, you have a lot of loop gain, and it behaves as though, I mean, a rough, this thing is, when we come to op amps, you will see that you analyze your circuit with ideal op amps, you will get some result. And then when the loop gain is very large, it will behave approximately like that. When the loop gain drops off below 1, then I mean, there is no feedback. Okay. It's like having some open loops. So the omega u by k, what I was getting to was, this is not getting omega u by k to be the closed loop bandwidth. It's not a coincidence. It happens to be that because that is also the unity loop gain frequency. Okay. The expression may be different. It's not that it will always be omega u of the integrator divided by the gain that you want to achieve and so on. But whatever the unity loop gain frequency is, that will be the limit of the ideal behavior of the negative feedback system. Okay. So the closed loop bandwidth will be the unity loop gain frequency. Is this okay? So we'll continue from there. Just think about this. This is in every negative feedback system, it will be like that. You will see that you will have various numerators, but in any negative feedback system, the transfer function will be something times L by 1 plus L, which can also be written as that same thing times okay, it's the same, right? So now you can see that what is this part? This is not 1. I mean, I just meant to put a dot there. What do I mean by ideal? It's basically whatever you intend to using negative feedback. Okay. So that you get if L is much more than 1. In any negative feedback system, the transfer function will appear like this. You will have this L by 1 plus L factor times something. That times something can be anything. Okay. But the point is this L by 1 plus L becomes 1 when the magnitude of loop gain is very large. Okay. It doesn't matter how much it is. It can be 100 or it can be 150, right? That number will be approximately 1. Okay. So all the good stuff about negative feedback comes from having a very high loop gain. Okay. So our goal is to try and make as high gain amplifiers as possible while maintaining stability. Yes. We'll see. But first of all, this business of continuous adjustment of the output that naturally leads to the integrator, right? So this amplifier without any delay or without any phase shift doesn't even exist. Okay. So this continuous adjustment naturally leads to the integrator. That's why I like that. But we'll see what happens. I mean, if you cannot anyway have amplifier gain with no phase, that's not going to happen because there will be some delay always. Okay. And I think you already studied the effect of having too many poles, coincident poles, and so on. Okay. So there are stability that will come into picture. So we'll continue from there. Let me stop here at this point.